All right, so today our learning goal is to determine the limits of functions in the indeterminate form. So what exactly is the indeterminate form? The indeterminate form is when substitution of x, or any value, or any variable, renders 0 over 0. Whenever this happens, when we're evaluating limits, it's our cue that we have more work to do. So let's get into it. But first, here are some properties of limits. This is on page 40 in the Nelson textbook. And each of these limits basically represents different notation things and ways that we can split limits up. So the limit in the first one, as x approaches a of any constant, is going to be that constant. So that's saying that constant is going to look like a horizontal line. So it follows that the limit is whatever that value is for that line. In the second property, the limit as x approaches a, x will equal a, because you substitute it in and you evaluate. Now in number 3, we have the limit as x approaches a of f of x plus or minus g of x. This is more of a notational piece to show that if we have a composite function made up of many different pieces, we're evaluating the limit of each and every piece. So basically we've distributed the limit into the function and showing the individual pieces. This generally is not an issue for students, other than they forget to put brackets around the whole equation that we're working with. In the fourth step, we've pulled the c out just to show that we can evaluate the limit with the constant, or pull the constant out and multiply the value of our limit by the constant value. In number 5, same idea, it's the product. We're applying the limit to each piece of the composite function. In number 6, it's the quotient to show that the limit applies to the numerator and the denominator in the same manner. And then obviously you have to make sure you're paying attention to your restriction. And then finally, if we have an exponent, we can either apply the exponent before we do the limit or after. Either way, we get the same answer. All right, so now we're going to do some examples. So these examples are a little bit more basic. We're given two functions, f of x and g of x, and we're being asked to evaluate a variety of limits. So in this first one, the limit as x approaches 2 of f of x. I'm going to substitute 2 into that function, and I end up with 8. So nothing crazy going on here. Just substituting into our function and evaluating. And you'll notice I didn't write the limit because I substituted in. In B, as x is approaching 50 of -4, so the value will be -4. Here in C, we're going to have 3 multiplied by -1 squared, subtract 4, divided by 3 multiplied by -1 minus 12. So using BEDMAS, we end up with -1 over -15, which we will write as 1 over 15. So in our first 3 examples, all of the limits existed. But now here, if you'll notice, when we substitute in, we're going to have 3 multiplied by 4 squared minus 4 all over 3 multiplied by 4 minus 12. So at this point you should be saying, uh-oh, wait a minute. 4 would be a vertical asymptote for this function, so there shouldn't be a limit. And when we do our math, we are going to get 44 over 0. So therefore, this limit doesn't exist. So none of these represented the indeterminate form because we didn't get 0 over 0. We got actual values. So now, in our next example, we get the indeterminate form. If you substitute 2 into 4 minus x squared over 2 minus x, you will get 0 over 0. If you want to show that step, go ahead and do so. It's not necessary, but if you want to, you can. I am going to look at this function and think to myself, if I get 0 over 0, I must be able to simplify it so that doesn't happen anymore. So just like when we were evaluating as h approaches 0, we're going to do the same kind of thing. Except here, we're evaluating at a specific value of x, not a secant becoming a tangent. So if I look at 4 minus x squared, I'm thinking, oh man, that's a difference of squares. So I have 2 minus x multiplied by 2 plus x. Oops, that's not an x. So 2 plus x divided by 2 minus x. And then I'm very happy because that 2 minus x goes away. That denominator, I no longer have a denominator of 0. So I end up with 2 plus 2 equals 4. So this function, you should be familiar with it, would be a straight line of y equals x plus 2 with a hole at the point 2, 4. In our next example, now we have a radical. So what do you think we're going to do here? We're going to multiply by the conjugate. So we have multiplied by 1 plus the square root, that is a plus sign, not a division, of 1 plus 3x over 1 plus 3x. Because once again, if I substituted 0 into the original expression, I would get 0 over 0. You'll notice I only changed the sign between our terms. Nothing changed under the root sign. So since it's a difference of squares now, I'm going to get the limit as x approaches 0 of 1 minus, we want to make sure we're using a bracket, 1 plus 3x all over x multiplied by, oops, I forgot. Oh, wow. I'm not sure what happened there. Let's go back up here and fix this. So it's 1 plus the square root of 1 plus 3x. And that's what I'm going to have in this bracket. We do not expand because ultimately we're trying to make the x that we have there cancel. So now I have the limit as x approaches 0. I'm going to have negative 3x over x multiplied by 1 plus the square root of 1 plus 3x. The x cancels, and I'm going to be left with negative 3 over 1 plus the square root of 1 plus 3 multiplied by 0, which simplifies to give me negative 3 over 2. So we've seen one where we have to factor. We've seen one where we have to multiply by the conjugate. So our third example of the indeterminate form is going to occur when we have a fraction. So we're subtracting a fraction. In order to subtract a fraction, we need a common denominator. Now, before I do anything, I'm actually just going to rewrite it so that we have something that looks a little bit easier to work with. If you're comfortable leaving it with a fraction over fraction, that's fine. All right, so now we need a common denominator. So the first term I'm going to multiply by x. The second term I multiply by 3, and then my denominator is 3x. Here I have 1 over x minus 3, and I'm super happy because I notice x minus 3 cancels, so I'm left with 1 over 9. I just want to bring up, since we're doing a lot of canceling here, if I have x minus 3 over 3 minus x, if I cancel these terms, make sure you recognize that it's negative 1 that you're left with, because they're different by a factor of negative 1. So just keep that in mind while you're doing this simplification. All right, our second last example is going to deal with a function, and we're going to use something called substitution of the variable. Right now, when I plug in 0, of course, we're going to get 0 over 0. However, I can't factor this. I can't multiply by a conjugate because the conjugate applies with the square roots. So there must be something else that I can do. So I'm going to let u be represented, or represent, sorry, x plus 8 to the power of 1 over 3. So I'm going to sort of start subbing in as I go. I'm changing all the x's to u's. So instead of having x plus 8 to the 1/3, I'm going to have u minus 2. You'll notice I didn't write the limit as x approaches 0 because it's not going to be x we're evaluating, it's going to be u. I also haven't done anything with the denominator yet because the denominator is just an x. So I have to do something to help me get that. So this x inside the bracket where I have u equals x plus 8 to the power of 1/3, I'm actually going to cube both sides, because then I will have u cubed equals x plus 8. This new expression that I generated, I can now isolate the x and then I'm ready to replace my denominator, because x is equivalent to u cubed minus 8. So I got one final thing. I need to figure out what u is going to be approaching. I know x is approaching 0, so I'm going to replace x with 0 and solve for u. So we get u equals 2. So we're looking at the limit as not x, but the limit as u approaches 0. Again, not 0. It's x approaching 0. It has to be u approaching 2. So then I have the limit as u approaches 2, u minus 2. The denominator is a difference of cubed. So I'm going to have u minus 2, bracket, u squared plus 2u plus 4. So the u minus 2 cancel and leave us with 1 in our numerator. Don't forget the numerator. So then I'm going to have 1 over 12 as the value of my limit. So this question is probably one of the most challenging types that you have. It'll be worth 5 marks because there's several different things that you need to do. All right, our last example for limits in the indeterminate form has to do with an absolute value. So right now we want to figure out what this limit is, and then we're going to illustrate with a graph. The key to this question is recognizing if we remove the absolute value sign, we get plus or minus, because the absolute value has a positive value and a negative value. So now I'm going to split these into the sided limits. So the limit as x approaches 5 from the left is going to be negative x minus 5 over x minus 5, which simplifies to give us negative 1. And we have the limit as x approaches 5 from the right of positive x minus 5 over x minus 5. They cancel and leave us with a value of positive 1. So without doing anything else, what do we know about the limit as x approaches 5? It does not exist. If we sketch this graph, oops, that's pretty bad. If we sketch this graph, I'll actually pull out a grid to make it a little bit easier. Get it down here so we can actually see what's happening. Okay. So this is telling me that when x is approaching 5 from the left, we are at negative 1. Approaching 5 from the right, we are at positive 1. So as we've learned, since the limit from the left side doesn't equal the limit from the right side, these limits don't exist. All right, hopefully this makes sense. If not, come see me with any questions that you might have.